Welcome to this video. In this video, we will go through the definition of basic economic load dispatch problem and a simple numerical example. So the definition is written here. It means suppose you have a power system area like this and you have number of uh, power plants which are operating in parallel. Say this is plant 1, plant 2 and plant 3. There are 3 plants operating in this area and you have some total load demand in this area. Then how to allocate this load demand among these 3 generators such that the operating cost, total fuel cost is minimum. That is what we try to do in economic load dispatch. So in economic load dispatch, it deals with determining the power output of each plant to meet the total load or specified load such that the overall fuel cost is minimized. So this is the main point. So that the overall fuel cost is minimized. And we know that the generating plants or power plants can be mainly classified into these 3: hydroelectric plants, fossil fuel plants, or thermal. This is also called thermal power plants or nuclear power plants. And in the case of nuclear power plants, they usually operate at a constant power output. So we need not do any scheduling for them. Where in a hydroelectric power plant, there is no fuel cost associated. So this economic load dispatch problem mainly deals with this one, fossil fuel plants. There will be some fuel cost to be minimized in the case of fossil fuel plants or thermal plants. So there are some performance curves associated with the thermal power plants. One is input output curve. So this is a plot between the input fuel in British thermal unit per hour and divided by per with respect to output megawatt. Okay, in x-axis you have output of the power plant in megawatt, and in y-axis you have the British thermal unit per hour input power in British thermal unit per hour, and the conversion is given here. 1 watt is 3.4124 British thermal unit per hour, and 1 HP is 2544 British thermal unit per hour. So it is essentially a curve between input power and output power, which are expressed in 2 different units. Okay, then incremental cost curve. This is another important performance curve of a thermal power plant. So this here we have on the y-axis cost per unit, that is rupees per kilowatt hour. Kilowatt hour is the number of units of energy. Okay, so per unit energy, what is the price to be paid? Rupees. Okay, and on the x-axis you have megawatt. Then this fuel cost can be approximated as a quadratic curve given by this. If Fi is the fuel cost of the ith power plant, then it is given by a constant term Ai plus Bi into power output of the ith plant Pgi plus Ci into square of the power output of the ith plant Pgi square. The unit is rupees per hour. Fuel cost in rupees per hour. Then incremental fuel cost is derivative of this with respect to Pgi. dFi by dPgi is given by Bi plus 2Ci Pgi. This is obtained by differentiating this equation. Okay, then coming to economic load dispatch, neglecting, this is the first case 1. Economic load dispatch, neglecting losses and generator limits. Suppose we have n generating plants and Fi be the cost of the ith plant in rupees per hour and Pd be the total load demand, then we have to minimize the total fuel cost given by sum of the fuel costs of individual power plants F1 plus F2 plus etc. up to Fn. This is the total fuel cost. We have to minimize this subjected to the constraint that total generation meets the total demand. Total demand is Pd, total generation is Pg1 plus Pg2 plus Pg3 etc. up to Pgn. That is written as sigma I equal to 1 to n Pgi. Okay, and this constraint optimization problem can be solved using Lagrange's method. And in Lagrange's method, we will form a augmented cost function that is obtained by adding the objective function. This is our objective function plus lambda times this constraint part. This constraint is written in this form: PD minus sigma I equal to 1 to n, PGI equal to 0. Then this is multiplied by lambda. That constraint part is multiplied by lambda. Then it is added to the objective function, that is total fuel cost. Then to local minimum is obtained by differentiating this Lagrange's augmented cost function with respect to PGI and lambda. So when you differentiate this with respect to PGI and equate to 0, you will get one equation, and when you differentiate this with respect to lambda and equate to 0, you will get another equation. So L is written here. L is sigma I equal to 1 to n Fi. This is total fuel cost plus lambda into PD minus sigma I equal to 1 to n PGI. Then you differentiate this L with respect to PGI. So within Fi is a function of the power output of the ith plant PGI. So when you differentiate Fi with respect to PGI, you will get dFi by dPGI plus lambda into PD is a constant, it is independent of PGI. So when you differentiate with respect to PGI, that will become 0. Then this sigma I equal to 1 to n PGI can be written as PG1 plus PG2 plus PG3 etc. up to PGI plus etc. PGN. So when you differentiate PG1 with respect to PGI, it will become 0. PG2 with respect to PGI, this is 0, etc. Then only this PGI term, when differentiated with respect to PGI, it will give a 1. Okay, all other terms will be 0. So this is equal to, equated to 0. So you will get this equation after rearranging dFi by dPGI equal to lambda. This is known as coordination equation. So dl by the second Lagrange's equation, dl by d lambda equal to 0 will give you the original constraint itself. Okay. So the solving these two linear equations together will give you the optimum operating point. So for economic operation, to meet a particular load demand, when generator limits and losses are neglected, all plants must operate at equal incremental cost. That is mathematically written here. dFi by dPGI is incremental fuel cost of ith plant. So here I will vary from 1 to n. There are n plants. So all the incremental fuel costs must be equal to a constant lambda. This is known as system lambda. So one example is written here. We have two units operating with the fuel cost curves F1 and F2 in rupees per hour. It is given here, and the total where generation PG1 and PG2 are expressed in megawatt. How a total load of 80 megawatt will be shared among these two generators for economic operation. And there is a second part: how will a load of 120 megawatt and 180 megawatt be shared? So to do this, for economic operation, we know that dF1 by dPG1, that is incremental fuel cost of first generator, first plant must be equal to the incremental fuel cost of second plant, dF2 by dPG2. So you write F1 and F2, F1 and F2 are reproduced here. Then for economic load dispatch, dF1 by dPG1 should be equal to dF2 by dPG2 equal to lambda. dF1 by dPG1 is obtained by differentiating the first equation. dF2 by dPG2 is obtained by differentiating the second equation. So when you differentiate this one, this 120 is a constant part, it will become 0. 22 plus 0.05 into 2 Pg1, that is written here. Here, when you differentiate F2, you will get 16 plus 0.06 into 2 Pg2. Okay, so these two has to be equal to lambda. Then you rearrange for Pg1 and Pg2 can be expressed in terms of lambda. So you will get two equations. Then in the first case, total load is 80 megawatt. So Pg1 plus Pg2 should be equal to 80. Then you substitute for Pg1 and Pg2 in terms of lambda. Then solve for lambda. So you will get the value of lambda, 23.637 rupees per megawatt hour. Then you substitute it back in Pg1 and Pg2. You will get the value of Pg1 as 16.37 megawatt and 63.63 megawatt. You can repeat this procedure for the total load for 120 megawatt and 180 megawatt. So this is how we can do economic load dispatch, neglecting losses and generator limits. Thank you.